Hi everyone, this is Tina Tangachan and I'm doing my final project uh, that is a hurricane detector as a part of the deep learning course. And as a part of this, my problem statement that I'm trying to solve is detecting the developing hurricane patterns by using satellite images through multi-layered deep neural convolution networks using Keras and Python. And you can see the two images that we have here. These are satellite images of cyclones, and the other one, which is a non-cyclone image. We are using this kind of imagery to see if there is a developing cyclone. The technologies used include Keras, TensorFlow, Python 3, Jupyter Notebook, Windows 10, and I'm using NVIDIA GTX 1070 for this system. Data sources for the different images that you see here on the screen are from the Google Images, then weather.com satellite live pictures, NASA satellite views, and National Hurricane Center images. You can see the link below for the pictures. Installation steps involved here are installation of Python, pip, and then we first install the TensorFlow, and then Jupyter Notebook, Keras, and all the other related APIs that we see here for this particular exercise. Once the APIs are installed, then we configure the NVIDIA CUDA core with its drivers, and then we install the TensorFlow GPU version using this command here. The process flow for this project is uh, the first process I started with was to download the training and the test data satellite images, and then splitting them into different folders, one for training and one for testing. Since this was a completely new project, there were no labels associated with the satellite images. So a label was given to each image with cyclone Y and cyclone N in the label, followed by the dot JPEG or PNG file extension. Cyclone Y would be the images which would show that these are developing cyclone images, and cyclone N are the labels for those images which are non-cyclone images. Since this project needed a lot of satellite images, and there wasn't any handy big repository, what approach I used was I used image augmentation. I used the image data generator to build more data out of the existing training data, and by different scaling approaches, different zooming approaches, using three different iterations per image, generated multiple images, and moved them over to a new folder, and these images carried forward the labels of their parent images. So if the parent image was of a cyclone or a developing cyclone image which had an extension of cyclone Y or cyclone N, the newly generated images from the image data generator would also carry forward the suffix of cyclone Y or cyclone N along with its PNG or JPEG extension. Once these labels were moved into the new folder, the original test images that were used to create these new set of images were also moved into the new training directory. Preparing the training and test images involved certain steps, and that consisted of converting them into grayscale images from RGB scale image, and then reducing and resizing the images into 150 by 150 to accommodate for all different sizes of images available on the internet that were being used as a part of the training and testing. Once they were converted into the new set, the categorical columns. Labels were converted into categorical columns, cyclone Y and cyclone N, and were given the label indexes of 1 and 2. For each image, it had a label which was a categorical value of 1 and 2 based on the label name, whether it had a prefix of cyclone Y or cyclone N. These images were then sent through the two convolutional neural networks, CNN Model 1 and CNN Model 2, and then both the models were evaluated against their loss and accuracy. And the best model, in our case, Model 1, was selected and then was used for further predictions. This model predicted for certain image that you can see below that as of May 6th at 8 p.m., the Caribbean satellite image generated from weather.com was predicting that there was a possibility of some kind of cyclone developing in the Caribbean area. Execution and accuracy. The data was run for 30 epochs, and we trace the images. This below image shows the accuracy and loss for the two networks. We can see that the convolution neural network for Model 2 architecture with L2 regularization seems to have a slightly higher training accuracy and the testing accuracy as compared to the convolution neural network for Model 1. Training and testing loss for the CNN Model 1 architecture without the L2 regularization seems to have been much lower than the training and loss as compared to the CNN Model 2. So when you look at the two parameters of accuracy and loss, we can say that the CNN Model 1 has better performance over the CNN Model 2, and we move forward by selecting CNN Model 1 as the model for our project. Once the data of different images like the ones that you can see here, these are all images from weather.com taken at different images. The format of the naming is the month, the date, the year, the time, and the satellite that it was being used to take the images from. And we can see against each of these images how the model predicted. And we can see on 5/5/2018, the Mexico satellite was saying that there was a chance of high cyclone possibility, but the winds probably diluted around 5/6, and there was no more any more chance of cyclone. And similarly in the Caribbean area, we can see there was no initial bad weather around 5/5/2018. Caribbean satellites showed no possibility of cyclone, but as it came to 5/6/8 p.m., the Caribbean satellites were showing some kind of cyclone possibilities. And these are the images that were being used to feed into the neural networks to tell whether there would be a possibility of cyclone or not. In summary, I would like to say that if we train the network with enough images and try tuning the network further with time, we can use the system for many useful applications. Some of the major advantages from this system would be we can accurately predict hurricanes. Timely warning can be issued, managing communication on ground and water if there is any human life involved, and managing supplies and managing medical help if we have the insight on if there are winds of hurricane nature developing. We can use these pros and cons. We can use these image based systems to forecast hurricanes and take appropriate steps to save human and material losses. We need lots of training data with correct labeling to make this network more effective. So as a part of initial training, we might need even human intervention to label and train a lot of images of satellite images that are coming from different sources. and then run it through the network. These are some of the references that I used during the development of the project. So now I would like to give a demo of my project. The project directory involves these four directories: new, train, test, and validation. The training directory includes a lot of images of with different labels like Cyclone N, Cyclone Y. These are basically images which says these are satellite images, and they will show whether there is a developing cyclone or no, and the corresponding labels will identify the pattern whether there was a developing cyclone or not. This is an example of a cyclone, yes. So the neural networks are supposed to pick up these patterns and identify any of these kind of developing patterns in wind. The walkthrough of the code is as follows. Um, Once the directories were created, the data was passed through the image data generator. As a part of this, the input data was reshaped into more number of images, three iterations to be precise, and then we generated three more images from the existing images. These images had the label of Cyclone Y and Cyclone N in the name, and they were further divided into two categories, image 1 and image 2, based on these labels to be used in the model later. The process involved training the data and testing the images, training the data and testing the data, where the images were passed to the training data function and converted into the grayscale images and reduced into 150 by 150 images. Similarly, the testing data was also passed to the testing data function, where it was converted to a grayscale image first and then converted into a 150 to 150 by label. These images were converted into arrays and then float 32, and then the categorical labels were converted into vectors 1 and 2. This is the architecture for our first model, where we have 64 layers convolutional 2D network with 3 by 3 filter and ReLU activation, and the input is a 150 by 150 into one image, followed by a max pool layer, then again another convolution 2D layer with 64 layers, 3 by 3 filter, ReLU activation, then a max pool layer of 2 by 2, convolution 2D layer of 64 layers, 1 by 1 filter, activation of ReLU, max pool layer of 2 by 2, then followed by a dropout layer of 0.5. This is done to reduce any kind of overfitting. Then the convolutional 2D layer of 64 layers and 1 by 1 filter, activation of ReLU, and a max pool layer of 2 by 2, followed by a dropout layer of 0.5. Finally, a layer for flattening is included, and the layer for dense 512 is included with activation of ReLU. The outputs are then passed through a dense 3 layer, which is activated by a softmax function. This is the actual summary of the model. The model was compiled using the categorical cross-entropy loss function, and the optimizer used was the RMS prop with a learning rate of 1e raised to power minus 4, and the matrix used was accuracy. The model was trained, and the different kind of accuracy and loss were saved into the history variable. The model was fitted for training set and validated against a test set for a batch size of 15 and 30 epochs. The final recorded loss for this model is 0.427 and an accuracy of 0.84. This is the architecture for model 2, where you have 64 layer convolutional 2D layer with 33 by 3 filters and ReLU activation, input image of 150 by 150 and 1, that is grayscale image, a max pool layer of 2 by 2, convolutional 2D layer of 64 3 by 3 filters with an activation of ReLU, max pool layer of 2 by 2, convolution 2D layer of 128 layers with 3 by 3 filters and activation of ReLU, max pool layer of 2 by 2, convolutional 2D layer of 128 with a filter of 3 by 3 and activation of ReLU, max pool layer of 2 by 2. Then it was followed by a flattened layer and dense 512 layer with the L1 L2 regularization and a learning rate of L2 regularization of 0.001, and the final dense layer with three outputs with the activation of sigmoid function. It is compiled using the categorical cross entropy loss function, and the optimizer uses the RMS prop with the learning rate of 1 into e raised to power minus 4, and metric used is accuracy. Below we can see the plot for the accuracy and the loss, where we can see the L2 model tends to have a slightly more accuracy than the non L2 model, and the loss for the L2 model is much higher for the training set as compared to testing set as compared to the loss for the model 1. Thus, we can conclude that Model 1 is a better fit for this project, and we proceed further with the predictions using Model 1. When we are predicting the data, we first pre-process the new images by passing it to the process pre-data, where we convert it into grayscale and a 150 by 150 image, and pass it through the predict function, and this is the sample of the prediction outputs that we get. Like the Caribbean satellites are saying that there are chances of cyclone, but similar Caribbean satellites were not reporting any kind of cyclones on 5.5. And we can see Atlantic region satellite imagery, radar imagery, do not show any kind of activity for hurricane, and the Mexico region satellites do show around 5.5 some possibility of cyclones, but then as we move towards 5.6, there are no chances of any kind of cyclone in the Mexican region. This is the final layers inside the different convolution layers, how the data is getting picked from by the different layers within the network, and we can see they are kind of focusing on the edges of the cyclone winds to detect these kind of patterns. Thank you for being a part of this demo. Uh, Thanks.